All right, let's get started. All right, let's get started. Yeah, Friday, 9 a.m. is tough. I'm hoping the 9:05 makes it a bit easier, but yeah. Anyways, welcome, good morning. Today's lecture is part 2 of Modern ConfNets. And this is what we'll be covering. So first of all, I'm going to give you an overview of what we mean when we talk about deep embeddings, latent vectors, vector spaces, manifolds, all of that stuff. Then we're going to talk about a couple of popular convolutional neural network architectures, including the reasoning behind them, why they're still important, and why they are important. And we're going to finish off with some architectures which use them, which can do things beyond just object recognition in an image. For example, they can localize objects in an image. All right, so about this deep embedding. So the way we tend to think of it is as dimensionality reduction. So for example, if you have an image that has 3 color channels, right, like an RGB image, and is of size 224 by 224, you have a 150,000 dimensional input overall, right? So you can take this image, wrap it around, simply write it as a vector which has 150,000 entries, which is a lot, right? What now the neural network does, and note here we typically denote a neural network with this sort of trapezoid shape because as we talked about last time, you have these max pooling layers or pooling layers in general. So the spatial dimension of the features typically gets reduced in the network. And what you, in the end, have is a very low dimensional vector. And by low, we mean like typically, for example, 2,000 or 4,000. In the case of an AlexNet, it was 4,000 dimensional. And after this embedding, after this, we have typically the classification layer, which gives us the 1,000 dimensional output. Now, the 1,000 dimensional output, of course, has information as well, but that's already very specialized and is exactly for the task that you're training on, because that's the one where you apply the loss to. But besides this one, there's a couple more. Like, you can use any deep representation and use them. We call them hidden or latent representations, and they are the representations which are inside of a network. So if you think about this process of going from this high dimensional input to this lower dimensional output, we need to remember that the inputs are simply raw pixel values, right? Like really, really, really uninformative, basically, if you look at them on their own. And here the outputs are what you want, like really interpretable, they're class probabilities, you have predefined the class names, etc. So the question is, what needs to happen to get from all of these weird pixel values that can change rapidly if you're like at the edge between background and object to this nice higher level representation. And by high level, you can replace that word with more abstract or more semantic. Semantic basically means it has more meaning. So all of these words typically get used in the same manner. Yeah, as I write here. So what we need is basically a process which goes from all the way to the left to the right, which gradually increases such information. And in so doing, it typically, or it naturally reduces the information that you don't need. For example, the exact color of the background, if you're training for object classification, or the exact size of the snout, for example. The presence of a snout will still be useful and is probably contained in that last deep embedding, but exactly the size is probably not necessary. And this is exactly what neural networks do. Like the nice thing is, and the logical thing is, they learn to do this automatically. You don't have to tell them, early layers, please just learn low-level information. High levels, please learn high-level information. It naturally does that. And yeah, that's kind of a different perspective on this thing we had last time where we said neural networks, what they do is they also learn the features. Well, they learn the features and they do it in a hierarchical way. This figure is quite nice to illustrate the point. So this lower dimensional space is also often called a manifold. And if you look at this manifold here, what you can see is that here the rotation of the digit simply means going in one direction of this manifold. And manifold here, it's visualized sort of as a 2D plane lying in a 3D space. What we mean more like is a 2,000 dimensional plane lying in a 150,000 dimensional space, right? That's what we had earlier. But here it's just for illustration purposes. And yeah, size changes in another direction, very nice. Think about the RGB space, you don't have any of this structure at all, right? You plot this in a, let's say these digits are 32 by 32 size. You plot any point in a 32 by 32 space, and you go slightly to the right while you're not doing any meaningful changes here, like changing 1 pixel's color or something like that. Versus here, you're doing some meaningful transformations when you move along the manifold. And actually, this is also what we see, and it's sort of something that you'll end up doing in the last assignment as well, actually. Finally, we can also take empirical evidence of what these neural networks learn. So here we already have the filters that we talked about the last time. We can also pick out individual image pieces that maximally activate these neurons. So you have, top left, you have these 9 neurons, 9 filters. And now we show 9 image patches each that maximally activate this. So you can clearly see what activates the top leftmost neuron are simply edges which go from top left to bottom right, for example. We can do the same thing for neurons, for some random neurons in layer 2 or in layer 3. And you can see also that the patches get bigger because now the receptive field is growing because they're deeper in the network, right? And it's a convolutional neural network. And you can see they're fairly consistent. They contain like, they are very specialized. So at the early layers, they're just edges. Second layer, they're like, okay, edges or like slightly more complicated patterns. Already at layer 3, you're seeing like, for example, almost something that resembles a tire detector or something that resembles flower, or I guess it's a mushroom, but yeah, at the bottom right, a mushroom detector or person detector, basically, without you having trained this. Yeah, like that.
Are these examples of images that give high activation, or are
Yeah.
these the images that give the highest in theory? Because they look very specific, right?
What do you mean, very specific?
The first one in layer 1 looked like abstract features that are learned.
Yeah.
But in layer 3, we see persons with like very...
Yeah, no, these are all patches which exist in the input data.
Okay.
So the big ones, right? Except the one all the way to the left. Yeah, so I mean, if you have a data set of 50,000 images, and here we're talking about, I think, 13 by 13 patches, you will have plenty of these patches, right? Even though, I mean, they're like magnified to be, they're usually not that big, right? Like, they're really, I mean, some of these patches you can probably see in all of these images, right? They're literally just some edges, basically. Yeah?
Yeah, I had a question. I'm not sure it's related, but like 5 years ago, there was a lot of talks about adversarial attacks.
Mm-hmm.
You could just change a couple pixels and then change the label.
Mm-hmm.
I was wondering if you could comment, like, has there been more research there? Or has there been more conclusions? We have more robustness?
Yeah, we can talk about it in the break. I think it generally refers to this manifold thing that you can easily, or like neural net. Or the main point is, I guess, neural networks are highly nonlinear functions, and so if you change the input slightly, you could end up somewhere completely else if the neural network hasn't been trained for that. There has been some progress, but yeah, it doesn't have much to do with this part, so we can talk about it later. Right, layer 4, layer 5, similar conclusions, and actually you get the same if you train methods in a self-supervised manner as well, so it really, you don't need to have label information. Like a neural network will learn structure, well, if you give it a good self-supervised loss, but like neural networks can learn these structures pretty much by themselves. Apart from this qualitative evaluation, we can do a numerical evaluation, which is called linear probing. So what we'll do here is we have a network like AlexNet, and we'll exit this network at different locations. So imagine you've trained your AlexNet on some data set using some loss. Now you want to see, okay, how good is the representation after layer 1? How good is it after layer 4, etc. So what we'll do is we keep the backbone frozen. So we're not going to change any of these parameters. And then we simply exit at various locations. For example, after layer 1, we exit, and here the spatial dimensions would be 55 by 55, which is a lot. We're simply going to pool this to 10 by 10 and then flatten it. So now you have a vector which is 100 times 96. So you get at the bottom, as I'm writing, you get this 9,600 dimensional vector out of here. And now what you do is you train a linear layer on top of this 9,600 dimensional vector. And this linear layer is trained supervisory to predict, for example, ImageNet classes, 1,000 classes. And now how good this linear classifier will do depends on how good the features are that are incoming, right? Because a linear classifier really can't do much. So unless the features are already good, the linear classifier won't give you very good performance. And you do the same thing at these other locations. Note that we're sort of changing the pooling size here because the inherent dimensionality of the network is increasing. After layer 1, it's just 96 dimensions. After layer 5, the hidden dimensionality is 256. So we want to roughly keep the sizes of the linear layers constant, right? And it's not quite constant, but roughly at least. Because if you just have a bigger linear layer, it has more parameters, it could learn more. That's why you want to keep this roughly equal. And what you see is the following. You can see that for ImageNet, for example, if you take a model which was trained on ImageNet, and then you evaluate it, okay, how good at various stages are the features for predicting ImageNet? You can see that indeed, the deeper you go, the better it gets. And I'm just adding another evaluation here, which is a randomly initialized neural network. You get first of all, you get not zero performance, right? You get 11%, zero, or chance performance on ImageNet would be 0.1%. I mean, your chance you wouldn't expect, right? Because you're at least training a linear layer. But you actually get some non-negligible performance of 17.1. So yeah, what you see is deeper representations, not only from the qualitative side, but also from the quantitative side, contain more semantic information, and even randomly initialized neural networks extract some useful features. All right, I'm going to ask you to do some small wake-up exercise, basically. Let's take 1 or 2 minutes, and please discuss with your neighbor or neighbors if you're sitting a bit with distance. What was the key concept that we talked about? Try ideally using your own words and don't use embedding, but say okay, yeah, whatever, however you want to describe it. Some pointers could be also what do you find intuitive and what do you find difficult to understand. All right, wake up. All right. Are there any questions which came up during your discussion with your neighbors? Yes? Guys, people, please.
So we're not really sure what the manifold is because one of us is saying that it's so the manifold was like a sort of dimension. One of us is saying that basically when you use the manifold, even though all those fours were rotated, they just that's just one of the features. So it's all just one four. Is that it? Is that the manifold?
So the idea of that picture was if you take rotated pictures of the four and you look where do they end up next to each other and they end up in like a line the more you rotate. So you end up having meaningful directions in the embedding in the manifold. And also like mathematicians use manifolds slightly differently, so I tend to say embedding, but yeah. Anything else? Yeah?
Yeah, I was wondering if you can tell us again what do C1 to C5 stand for on
Classifier 1, classifier 2, classifier 3, basically.
like different classifiers?
So the C1 is trained on the features after the first convolutional layer, basically.
Okay.
Yeah.
That's it.
All right. One thing to think about is also that what I showed you here was evaluating model trained on ImageNet on linearly classifying to ImageNet. It would be better if you instead evaluate it on a different data set. You train it on one data set, you evaluate it on a different set, because then you're actually measuring generalization. All right, yeah.
So C1 stands for like the linear layer, like the linear layer is what?
Yeah, so C1 stands for a linear layer trained on top of the features that came out of the first convolutional neural net layer. Yeah.
It's 11.6, not 17
For that one, yeah. Yeah. Yeah.
When you said they didn't use a different test set, did you mean like it was on the same images, or was it just from the same data set? They should have like got it from the
Well,
data sets.
Well, what I'm saying is like, it depends on what you want to measure, but if you want to measure generalization, it sort of makes sense that if you train a network supervisedly, then of course the deep layers are closer to the final representation you want, closer to the loss, basically. But if you just want to measure how good are the visual or how generalizable are the visual embeddings you're learning, then you should probably test it on a different data set as well, which is done regularly. All right, so let's after this one, let's recap. So we had last time these sort of things. Today, we're going to be doing more of this, basically. The reason is because there's a bunch of important principles behind these other architectures that we're going to talk about. And because even though some of them are don't give you the best performances, the principles that were introduced in them basically live on, and even some models remain state-of-the-art in some niche. All right, so we're going to start with the VGG network, which stands for Visual Geometry Group, which is a computer vision group in Oxford. And what they did is they made a network which was basically the next AlexNet. What they managed to do is train a neural network, a convolutional neural network, which has 16 layers. So a lot deeper than what AlexNet had. And the overall architecture is here. By now, you understand all of it. You have convolution, ReLU, max pooling, and then a fully connected and a softmax output. Crucially for VGG, the spatial resolution is preserved. So we had this last time. If you pick this sort of magic combination of filter sizes of 3 by 3 and a stride of 1 and a padding of 1, you exactly reproduce the input size from your filter. And other than that, there were no fancy normalizations, simply going deeper with these simple 3 by 3 weights, which, as it so happens, look like they're really tiny, right? 3 by 3 filters. So why did they go for these 3 by 3 filters, which you cannot interpret, which are like really small? Apart from like they could have just kept it at the deeper levels, right? Well, there's a couple of things you can. A 3 by 3 filter is one of the smallest possible filters to capture, relatively speaking, to the main patch in the middle, up, down, left, right directions. And if you combine two 3 by 3 filters, you have a receptive field of 5 by 5, as illustrated here. And importantly, well, or you can have 3 of them to have a 7 by 7. So what you're doing is you're replacing one large filter with, or if you do that, you're replacing one large filter instead with 3 of them, for example. And now you could add a nonlinearity in between them, which means your neural network will effectively be even more nonlinear, which is exactly what you want. You want them to be deeper. And crucially, you actually save parameters while doing that. So the calculation is here. And if you have deeper layers, like making a neural network deeper, as we had earlier, with a hierarchy and the different things which get learned have benefits as well. So the neural network now isn't forced to learn everything within a few layers, but instead can spread out what it's learning across a few layers. So that gives you performance gains. It doesn't stop with 3 by 3. So VGG was also one of the first neural networks which use these 1-by-1 convolutions, which we talked about the last time, which simply mixes the features within each location. And so you do this at every feature map location. You simply slide this across, basically. The resulting output shapes and sizes are given here. On the right-hand side, you can see these different variants of the VGG network. So typically, people make various variants depending on how much parameters you want to be using or what kind of target performance you're looking for. So you can see in table 2 at the bottom, you can see these have like slightly different number of parameters in terms of millions of parameters. Here are the training details. Here they used a learning rate schedule, which basically decreased the learning rate by a factor of 10 as soon as validation accuracy stopped improving. So that's sort of a automatic learning rate scheduler in a way, which is, of course, by now a bit outdated. Since the network uses max pooling, and we talked about this last time as well, max pooling means the high values are the ones which carry the information because they are the ones which get through to the next layer, which is great because now we can just visualize the values that are outputted for different filters at various depths. And you can see, first of all, going from top to bottom, that indeed the spatial dimensionality or like the spatial resolution is decreasing because we have these pooling layers. So every time the spatial resolution is decreased. So you have this trapezoid shape, if you were to plot this as a diagram, basically. And you can see that the network is focusing on some important regions, like the edges. It's like almost not at all focusing on the blurry background in the end. Although, like not all of these are really interpretable, right? Some of them simply focus on the edge of an image at the end. So that's not really state of the art of interpretability. Yeah. Uh-huh.
And the most left thing seems
Yeah.
to be all zeros.
Yeah.
That seems to be like all bad neurons.
Yeah, not that this is just for one image, right? So perhaps that neuron only fires for dogs, let's say. And we're only visualizing a few random ones here, so. Yeah, but good point. It's always good to check these. Another method, apart from picking out the patches which maximally activate neurons, is something different. So I'll first show you how it looks. So for example, for the same stuff, you can be instead generating images that maximally activate these neurons. And for example, for the later, well, you can see that it goes from simple edge or like one-directional patterns to like slightly more complicated patterns, patch structures in the bottom left, and then in the right, like even more complicated structures. And towards the end, you can actually see some objects, for example. In the bottom right, you can see the lamp pretty much from this image. These are pretty fun to look at and kind of look like hallucinations. And they're done in a very simple way. So now you have a network and you want to find, okay, what would maximally activate my output neurons? Let's say what would maximally output the lamp neuron. So what you do is you start from a blank image. And this input image has, instead of having RGB values, it has parameters, vectors that you can learn. And now you try to increase the score in the final layer that says it's a lamp simply by doing gradient ascent instead. So you're trying to increase you're changing the pixel values essentially to increase the value that you get at the end. And nowadays there's some hacks that get additionally used, so you get like even prettier illustrations as I added in like the further reading of last lecture from distill.pub. But yeah, this tells you a bit what the neural network is looking at. Yes?
Is this the same visualization that was used in this Google Deep Tree
Yes.
videos?
Yes. Yeah. Yes.
Are the colors interpretable in any way?
They should be, technically, yes. Yeah. But note that neural networks often don't care too much about the exact color. In fact, like often one of the most popular augmentation methods is heavily jittering the color. So like changing the brightness extremely sharp and other color values. So typically they look more at like patterns, not that much color. So that's why the tennis ball might be, I mean, it's clearly bright, so it has learned that, but it's sort of picking it up as yellow, as green, yeah.
Are these local optimally?
That's a good question. Yeah. I mean, you would certainly find an image that would better activate this neuron, yeah? And you would also, there's ways which can regularize this image to look more like real images, for example. But what you can also see here is that it clearly doesn't care, or like if you want to maximally activate this stuff, yeah, you're just putting more objects in there, right? Like if you want to maximally activate the tennis ball neuron, you're just putting 20 tennis balls in there. Yeah, or with a husky, you're getting like 10 different husky ears, but not like a full husky, for example. All right, next network. It's called the inception network. So the idea that this neural network architecture is addressing is the following: that you want to do object recognition, but sometimes the sizes are quite different of the images of the objects that are depicted in the images. So what you would need is that also the receptive field should vary in size accordingly, right? So if there's, let's say, an ear detector in layer 3, then for the first picture, it's only seeing a part of it, and for the last picture, it's seeing the whole dog, which is quite tricky. And so this ear detector, let's say, that gets learned automatically, would have to do all of these things at the same time, which is really difficult. So what you do, you want to learn different convolution sizes, but stacking them naively is pretty expensive. So the main idea would be the following. You simply have a bunch of convolutions, so you have a 3x3 convolution and a 5x5 convolution, which give you like these different sort of sizes, and then you concatenate them. Concatenation, I hope you know, simply means like putting it together. So if one vector is 100-dimensional, another is 200-dimensional, after concatenation, you simply get a 300-dimensional vector. And if you do it like this, well, the good thing about this sort of idea is you're kind of hedging bets, right? You're having multiple convolutions. You might not know which one is best for any given image, but you're having all of them. But the problem is if you do it like that, it's pretty expensive. So the 1x1 convolutions, again, come to the rescue. So with the 1x1 convolutions, you're reducing the size, the dimensionality that is not depicted here. And then you can apply the 3x3 convolution, and then at the end you can do the concatenation procedure. The overall network looks as follows. It looks quite colorful, first of all. It's now 22 layers deep, or even 27 if you want to count the pooling layers. At the end you have a global average pooling. And importantly, so this is the inception module that we just talked about, so you can look at it from this perspective, and you can see again the 1x1 convolution. What you're seeing also is something that was introduced in this paper for the first time, which are these auxiliary classifiers. So if you go all the way to the right on this plot, you can see the final output, right? That's where the loss is applied. But you can see, in addition, there's like these two losses which are applied. One is zoomed in here where it says softmax 0, which means like a supervised loss is applied. So this is kind of like the linear probing we had, except that here the purpose is completely different. Here the purpose is actually to propagate gradients into the main network. And the reason is because if you start making it deeper this way, you have the vanishing gradient problem. So again, the reasoning is, yeah, the deeper you go, you always multiply, you end up potentially multiplying small values by small values, which ends up at something that's extremely close to 0 or very low, which means you're training very slowly. And so this auxiliary classifier simply gives you a fresh gradient, which is high because it won't be able to classify it very well at an earlier layer. And remember, earlier layer means late in the backpropagation procedure. Right, so these are depicted here. There's a bunch of upgrades to this network. One of the main things is that instead of using an n by n convolution, you can use one n by 1 convolution, add a nonlinearity, and then apply a 1 by n convolution. So yeah, splitting the filter basically between the two directions. And the networks have been made wider, and wider means like the dimensionality has been increased. Deeper means that, right? The number of layers. And batch norms have been incorporated, etc. Yeah?
Are n by 1 and 1 by n filters in sequence as expressive as n by n filters, or less, or does it?
Homework, yes, that's a good question. Yeah, I mean, I can give the answer at the end of the lecture. I think it's an interesting thing to think about, yeah. One hint might be an n by 1 filter has n parameters. Another one has, again, n filters. N by n has n squared, so you have less parameters. So, I mean, that probably gives the answer already. But so, yeah, you need to compensate for more. If you do this and you don't want to get a hit in performance, you need to compensate for more dimensionality, doing something smart. All right, before we go to resonance dense nets, I want to show you the following, which is actually taken from my previous supervisor who gave a deep learning lecture at some point. So we had this AlexNet, right, which is depicted here all the way, including the fully connected layers. Then we had VGGM and VGG16. It's already, okay, 16 layers. Then the people at Facebook said, we need to go deeper. Actually, he didn't have that one in his slides. I added this one. But and then we ended up at GoogleNet with like 22 layers. And then we're now going to talk about ResNets, which are basically here. So ResNets in their original form went up to like 200 layers. So here it's only depicted 152. But actually ResNets, as we'll speak later, have been trained with thousands of layers as well. So from this plot, like the important thing is, why do we even care? Or from this whole lecture, maybe even today, why do we even care about architectures? And the reason is the following. So you have here depicted in the left plot the top 5 error. So you want this to be as low as possible. And you can see it's nicely decreasing the more modern you go with your neural network, just as the accuracy is increasing. However, the number of parameters stayed more or less the same. I mean, apart from this spike there, but which means it's really smart to have better architectures, right? You have better efficiency, you have better performance, and quite often you have better other attributes like robustness or transferabilities. And there simply are better architectures for a problem. For example, if you think about using a CNN versus an MLP for images, the CNN will always win. But then within CNNs, of course, we have all of these variants. So the question is, okay, what is really the best architecture, so to say? And you can define best in various terms, like very easy to optimize or gives you very high performance given the number of parameters, etc. And that's why we have all of these. And depending on your definition, you end up at various neural networks which exist in various networks which we're actually talking about today. All right, with this sort of motivation, why we care about architectures, let's talk about ResNets. So yeah, it was one of the first really deep neural networks where they showed that you can train a neural network for up to 1,000 layers. But that's not really why we care about it at the moment anymore. Like, no one uses 1,000 layer deep neural networks. Why we care about is because it introduced a new concept, which is called residual connections, which we're going to talk about now. It got pretty good. At the time, it got the best ImageNet performance, and with that backbone, you can use it for object detection, segmentation, etc., and it got really good performance. The motivation for this paper was the following. The question was, so clearly we want to go deeper, right? And if you simply have two neural networks which share the same weights, this is the red part, and you make the network B simply deeper. It could always, if it was an identity layer, it would perform equally well. And in fact, if you let it be a fully connected layer, it could, if it doesn't want to make it any deeper, it could always learn an identity, right? A fully connected layer can always do that. So technically, just if you initialize it like that, it should always be better. Like, there's no way it should get worse. And you could say that actually, like, whatever ConvNet A can learn, ConvNet B can learn, basically. So these can learn these, but in fact, what you're seeing is the opposite. You're seeing that a 56-layer neural network not only gets a much higher training error, but in the end, that's what you care about, also gets a higher test error, which is really strange. And so the question they tackled is, why is this the case? Because if you can solve this, you can train deeper neural networks. So what you saw is the following, and what they called it performance degradation. And they figured out that it's mainly because the optimization is just harder if you have more depth added. It's your optimizer ends up not finding the right solution. Yes, it could learn this identity if it doesn't need it anymore, but it's just extremely, extremely difficult. So the main finding is that, yeah, not all network architectures are similarly easy to optimize. So what they introduced is this trick to make it easier to optimize. Yeah, the reasons for this degradation, or why it stops learning and why it has a more difficult time to find this, to find an optimum, yeah, something like the stuff we talked about earlier, right? Like, if you have more layers, the gradients can get lost. You might not get very good gradients, etc. They didn't focus too much on that one, actually. They were very engineering and said, okay, we're proposing a way to fix this, which is this residual idea. So let's say we have this neural network with a nonlinearity, or like just a layer, for example. And the idea is perhaps we should instead of learning this whole thing, let's learn how we need to change it. Because you can say instead of having to learn the magnitude and the direction of the activations that we need to change, we're simply going to learn the difference. So the following. So instead of having simply the next output of the layer be a equals f of x, you're going to say the output will be h of x equals f of x plus x. So let me write this down here as well. Right, so this is pretty simple. And so what this means is, what this neural network is learning, therefore, is simply h minus x. So this is the delta that I talked about. We can call this delta, or we can call it the residual. So it's simply learning, given that I'm getting this additional input added, what's the difference that I need to learn? Right. So it looks like the following. Here are a bunch of versions, but if you focus on the bottom left, for example, you can see f of x is now like two conv layers with a ReLU in between, and then this identity mapping, which is simply bypassing this nonlinearity, bypassing this f of x, and going back to the computational graph and adding it. Right, and sometimes if you, for example, have different dimensionalities that you want to achieve, you add a one-by-one convolution. Yeah. Or if it's about spatial stuff, then you can add zero padding. And with that, they actually were able to train the 34-layer neural network. So on the left, you can see before, and on the right, you can see after. Now the 34-layer neural network actually performs much better than the 18-layer neural network. And with that, they showed that they can train much deeper neural networks. They were able to beat benchmarks by a lot. And by now, like one of the most used neural networks and is a standard for everything for computer vision is the 50-layer version, ResNet 50. So that's like really, if you want to do anything where you say, where you show something, you typically benchmark on this one, at least on this one. Yes?
So they solved the problem of residual connections.
Mm-hmm.
Why the first case didn't work? Like why the addition of identity linear layers degraded the performance of the network?
Well, it's just very difficult. I mean, a normal neural network could learn something like that, but it's just very difficult to optimize. Like the optimizer doesn't find such a solution. So it's really about optimization. It's not about necessarily architecture per se, but having these residual connections. I mean, you can, if you just do like the gradient here, you can see that this gives you a 1, right? So you get like the gradients flow perfectly through this residual connection. So whatever you're doing here, doesn't matter. You can have the gradients flow through this connection all the way. So the gradient flow is optimized by a lot by these residual connections. Yeah?
Does this have a big impact on your initialization of the link matrix? Because I feel like that improves.
Good point. You might want to check it. But also, these networks have batch norm. So they're much more robust against this. And there's a couple of variants, actually, which all have to do with where you put the batch norm. So yeah. And there are these variants. You have another innovation, which is called ResNext, actually, where the basic idea is you use grouped convolutions, which we talked about earlier. So instead of having something that looks at all the channels, it only looks at a subset of channels. And this way, it gives you efficiency. And again, you see this trick of one-by-one convolutions here that reduces the dimensionality to 4, which is very low, but you're having 32 of these running next to each other, basically. So it allows you to, again, have all of these different convolutions running, and yeah, having somewhat like this inception-looking graph, except that now the modules are the same size. Right. Yes?
So regarding ResNext,
Mm-hmm.
in general, they say that it has better performance because of better initial training dataset because it was made with Facebook. But you discussed about the different architecture. Do you think that which one is the most important for ResNext specific?
I mean, all of these benchmarks are typically, or not typically, they're always trained on the same data set in the end. So if a model just gets better performance because it was trained on a better data set, then people wouldn't care that much. You always need to show, given the same data set, it gets better performance. And ResNext does give you better performance, but it's also a bit slower, for example, if I remember correctly. It saves you a bit parameters, but it runs a bit slower. Yeah, it really depends. It just so happens ResNet 50 is quite a standard one that like everyone is sort of familiar. It's not state of the art in many things right now, but it just everyone's familiar with it. So it really depends what you're doing. If you want to push the numbers, how good you can get with, let's say, 50 layers, you might want to go for ResNext or like more modern architectures. Yes?
What causes it to be slower if it has less parameters?
It's all of these operations that you need to do in between. So, for example, imagine something like you, where did we have this? So yeah, we had this pooling operation, right? You pool something to 10 by 10, and then you flatten it. And then you do something, and then let's say you reshape it to 20 by 10. All of these reshapes and flattens, all of these things where it only looks at specific parts, they don't have parameters, but they still cost computation, for example. All right, and here, yeah, the observations that the normalizations were absolutely key for this one. And these residual connections are very, very important. And they live on everywhere. So nowadays, you have MLPs with residual connections. They are the key, or not key component, but they are in transformers as well, in multi-head attention, as you'll see next week. So yeah, that's one of the really important legacies of the ResNets. And with that, let's take a break until 10. Hey, yeah.
Hey, I have a question, just my question about like residual, where it was there. Like I don't get the intuition of residual and why does the addition of linear, of identity linear layer didn't work and decrease the performance?
Well, the idea of the additional linear layers is, like they will still get gradients, and they simply they make the neural network deeper, which means you have this vanishing gradient problem.
Okay.
So it's just really difficult to optimize. If you have a neural network, right, that ConvNet A, and you simply add identity mappings, which you don't train, yeah, it's going to give you the same output.
Okay, but if you train them,
If you train them, it's not going to be as good, yeah.
Okay, so and like with the addition of batch norm layers and all the techniques without the residual, it
Still,
would also
yeah,
work,
still.
or it's
Batch norm
still-
was around, like they use
but
that.
it was not enough to,
Yeah,
to solve
yeah.
them. Okay.
And the residuals just allow for really good optimization.
Okay, and,
Yeah.
and how and from where does it come from, the residual just
From this thing that the gradient, so if you're like,
just okay.
yeah,
Solve the
yeah, exactly.
Okay. Okay, great. Thank you.
All right.
It's basically going after that question, because why then do we still need batch norm? If we already say that the residual connection solves the vanishing gradient because the gradient's one of this connection, then why do we still need the batch norm?
Batch norm solves a couple of other problems as well besides vanishing gradients. Like it keeps the sizes of the activations more or less the same, so they don't drift in various directions throughout the neural network.
Yeah, exactly. So it makes it smoother and
Yeah,
easier to.
yeah. That being said, there are, like I think last year, some architectures like ResNets which can do without batch norms or any normalization layers actually. But that's very rare and that's very difficult. But it is possible. It's, yeah.
So for VGG, you said that we have auxiliary outputs.
For inception, yeah,
Inception.
yeah.
Does that mean that at the end we do some kind of averaging of these three?
Good question. No, you throw them away. yeah, you throw them away. There are some people which are interested in something called conditional computing, which means like, so for example, you could imagine an image of a blue sky. You can probably classify pretty well after like 2 layers, right? But an image of, or differentiating between that kind of dog breed versus that kind of dog breed, that might need 20 layers. And so there's actually some architectures which have something like this structure. And then if they're sure enough, they're going to say, 2 layers, enough, sky. depending on the image. But in this case, they just threw them away. They were just used for training.
Only for the backpropagation.
Yeah, yeah. Yep.
I have a question about these kind of sketches here. So do I understand correctly that all of these layers kind of are 64 by 64 and you use only max pooling to kind of up the layers? So you go, or the inputs and the outputs. So you go from 128 to 128, again another 128 by 128.
Not 128 by 128. Or you mean one? Well,
inputs and
two.
the
You
outputs
mean
of-
two? Yeah. So the spatial sizes are not written here, right? The 64 is the hidden dimensionality.
Oh, okay, so it has 64 hidden dimensions.
Hidden, yeah, exactly. The feature size is 64.
Okay.
So
256. Drops to 128. And then this is up to 512. And it drops after max pool, it drops to 556.
What do you mean 258, 256?
Before the max pool.
Yeah.
So it gets bigger, max pool gets smaller. Bigger, gets smaller.
Okay.
yeah, so typically what you do is whenever you make the spatial extent smaller, you make it deeper. The dimensionality is increased. That's a very
Okay.
typical
Oh, okay. Yeah,
thing.
makes sense.
So it's kind of the overall representation of the image is still like able to carry a similar amount in quotation marks of information. That's
Okay.
typically what's done.
Thanks.
Yep.
I also got something. I'm interested in AI safety, like interpretability, robustness, transparency. I don't really know what yet. Do you know anybody who works on that who might at some point turn into a supervisor or something?
Good question. I mean, interpretability, lots of people do a bit. Like I've also had one project on, or like two on interpretability.
Yeah, I guess
But-
you can apply it on
But AI safety feels like a special crowd in a way. So I don't know anyone, for example, personally
yeah, I
that is
feel like
working
this
at the
uni,
moment.
Like, I want to go in that direction. At this uni, I gotta pick somebody who's in
Yeah,
here.
yeah.
So I'm looking for the best, next
Yeah.
best. So maybe something like interpretability applied to, I don't know,
Yeah,
geometric
maybe,
or whatever,
but-
where there's an intersection.
But there's definitely, I mean, it's a huge topic right now. So there's All right, let's continue. So we're going to continue with a quick quiz. So on the right-hand side, you see the forward function of a generic ResNet block. The question is, what of these statements are true? Is it only 1/4 of the values of the out variable are non-zero after line 97? Is it writing line 102 as out equals out plus identity will not propagate the right gradients? Or 3, out self dot downsample calls a pointwise convolution. So have a think about these 3 things. And in the last question, just strike this out. All right. Thanks, though, for closing. But all right. On the mark of 3, you also have to do 1, 2, 3. Like now, right now. All right. 1, 2, 3. 2s, 3, 3. What do you say? Okay. So the answer is 3. So downsample calls a pointwise convolution because sometimes, and even in ResNets, you're reducing the spatial size and you're increasing the dimensionality. And if you increase the dimensionality, then this residual, you need to increase the dimensionality of the residual as well. So sometimes this one won't quite work. So instead, you're running like a 1-by-1 convolution of this, basically. And writing line 2 regarding point 2, that will work just fine. It doesn't do the operation in place, so it's slightly less efficient. And 1, I think no one picked, and that is correct. Just because batch norm followed by ReLU, well, first of all, after line 97, we don't have a ReLU, so it shouldn't be. And even if there was a ReLU, there's no guarantee that the stuff that got canceled out from the first batch norm followed by ReLU, that the next batch norm cancels the next quarter out. All right. As a historical note, before ResNets, there was actually HighwayNet, which is actually had a similar function, except that they didn't have a residual, but they were learning how much to propagate from the last layer. And it's kind of similar to LSTMs, which are a recurrent neural network structure, which has a property to forget versus keep activations from previous time steps. And here, instead of time steps, we're basically having this depth as a thing. All right. So now we're going to move to dense nets. Thanks. So here the idea is to add multiple skip connections. So clearly the skip connection idea worked. So you go all over the place and add them to everywhere, basically. But there's a good motivation behind this. So the motivation is if you assume that the first layer captures something low complexity like edges, for example, and the higher layers capture something more complex, let's say faces, then why don't you allow the last layers to also use some of these very low complexity features? So in a very crude example, you could say, okay, can you not have a layer that combines these? For example, that can model a face with like a very distinct scar, right? Which would be a layer 1 feature, and a face would be like, let's say, a layer 5 feature. But standard convolutional neural networks wouldn't allow for this. Like they might be able to implicitly keep low dimensional or low level features through this residual connection, but you're not explicitly modeling for this. So if you instead explicitly model for this and allow for these connections that go all the way from the beginning to all the way to deeper layers, you can model these more complex patterns. And indeed, this then looks as follows. So first you apply some convolutions, you get this feature map, and then you propagate the stuff that you're getting from the past, always you pack it to the next feature. So again, like you start with this, and you add what you had previously. Then you apply a new convolution, and you add what you had previously. And by adding, I mean concatenation. As you can see, the feature is gradually getting bigger and bigger. This factor of by how much it gets bigger is called the growth rate, and K. And depending on how you pick it, it can actually save you parameters. And dense nets give you really astonishingly good performances on some tasks. Again, they alleviate this vanishing gradient problem, just like ResNets do. And they give you pretty good performances. And that was sort of the state of the art for quite a while, I would say, or like one of the innovations when everyone was coming up with neural networks. Yes?
I think I missed it, but why do they opt from LSTMs? And LSTMs basically just learn that what to propagate forward and backward.
So highway nets are basically LSTMs, but instead of time, you have depth. But we're not talking much about LSTMs in this lecture, so we can discuss after the lecture. It didn't stop with DenseNet. So you can see DenseNet is AlexNet, where we started last lecture, is there. DenseNet, we're here. Now, VIT and SWIN is something we're going to talk about in the next lecture. But you can see the performances keep on increasing, i.e. the top error keeps on decreasing. And also note that here we're not measuring the top 5 error anymore. We're measuring the top 1 error. And this is, even though sometimes in ImageNet images you have more than one object depicted, but still mostly it's the dominant object. So top 5 error simply counts your top 5 predictions, and if one of them is inside, it will give you like a point basically. So it's always easier to get a higher performance on top 5. The number will strictly be higher than top 1 error. But even on this top 1 error benchmark, or like metric, you're seeing improvement steadily. A different network which is not in this benchmark, yeah?
One more thing, maybe to the DenseNet connections. You add the features, but they have different sizes. Do you need to do some rescaling to concatenate them meaningfully?
Yeah, you can only concatenate them when they have the same spatial size. So you do this at a given spatial size, yeah. So in sort of blocks. All right. Another important neural network architecture are mobile nets. They were the ones which really used what's called depth-wise convolutions to the full extent for getting networks which run on your mobile phone, which can be extremely fast. So what are depth-wise convolutions? The idea is you replace a standard D by D. So we talked about convolutions, right? So they have, so let's write a convolution function which has like D in, which is the incoming dimension, the outgoing dimension, and then the kernel size, for example, K by K, right? And what a depth-wise convolution does is first it applies a convolution simply on one channel map, spatial. So you have a spatial convolution first at every channel. So basically so what you have is a group convolution where every single one of these, so let's say you have 100 of these, and 100 of these. Now every one of these is simply looking at a corresponding one. Versus usually in a convolution you would have this channel looking at all the other channels, right? So you're saving some compute, you're saving a lot of parameters and compute here. with, of course, some disadvantages. But this is just the spatial part. So this is the first depth-wise convolution. You're including spatial information, but you're not mixing information between channels. So what do you do next? You concatenate the stuff, and now you mix channels. And so this is like just like we divided kind of this n by n convolution into a n by 1 and a 1 by n. This is very equivalent to that. So instead of having this basically k by c convolution, you're making a k by 1 convolution, and you're adding a 1 by 1 by c convolution after that, in broad terms. And this saves you a lot of parameters. Of course, again, you're getting a hit in terms of what you can do, but the performance is extremely high still. Like you can get top 1 accuracies of 70% plus, even with much less multiply and addition computations. And this is the overall architecture, how it looks. It's all about these depth-wise separable convolutions. Yes?
So 1 by 1 convolution is kind of in charge of like channel mixing.
Precisely, yes. So you could say you're splitting the labor. One thing is doing channel mixing, the other thing is doing space mixing. All right, another network, not super, basically not used for much, but the point is really important. So all of these benchmarks were done on ImageNet. This model, what it did is it trains a neural network that operates on very small patches, on 9 by 9 or 17 by 17 or 33 by 33 patches. And then it takes this network, which was trained on these patches, and simply slides it across the whole image. So you're having a fully convolutional neural network, and that operates on a very small patch. So the receptive field of this neural network is kept at 33, basically. And you do this by simply replacing the 3 by 3 convolutions, which gradually increase the receptive field. And you instead just keep 1 by 1 convolutions, and then you can keep the receptive field pretty small. And so all of this network does is it accumulates local 9 by 9 evidence across the whole image, and then it just sums it up. And then whatever has accumulated the most evidence, that's the prediction. And you can see that it smashes the performance of AlexNet. It almost reaches the performance of VGG16, which is not super high, but still it shows you that top 5 validation performance of like 87%. And if you look at these features from 9 by 9 to 17 by or 33 by 33 or something, you can see that for the 9 by 9, these are tiny features. We couldn't make sense of this, let alone predict which ImageNet class this is. So that was one of the papers which really told you that, okay, ImageNet might not be the way that we understand humans. And there's another paper, we understand images. We humans understand images. There's another paper which also goes into that direction. So let's focus on the right plot first. You have an image that just contains a texture. The model will say Indian elephant. That's fine. You have an image of a cat. It will say cat. Sure. Now, if we saw the rightmost image C, we would probably not say elephant, at least. We would probably say kind of cat, but the models will get it wrong. So this paper was another really important indicator that neural networks trained on ImageNet back then, still to a large extent now, they mostly focus on texture and not on shape. And you can quantify this. This is shown in the left-hand side. Humans, the red points are mostly on the left-hand side. They focus on shape. Computer vision models, they focus on texture instead, which is not quite what you want. You don't want to be classifying something as Indian elephant just because it has this texture. All right. Then we'll go to quick relaxation of how research gets done, part number 5. Right, so last time we had this realize and seek those, that's funny moments. Today, so once we found this funny, or we have an inkling that there's probably some interesting research that can be done here, how do we analyze this further? So I wrote this down sort of as, and again, always these series are sort of from my perspective, and they don't have any guarantee that they're complete and so on. But the way I would go about this is the following. First, establish some benchmarks, because if we cannot really know what we cannot measure, at least in this field. Establish baselines, because if you get 58%, like, is it supposed to be good or bad? We don't know if we don't have baselines. Just like we had this, for example, random neural network as a baseline. So if we get 17%, that would mean we're performing similarly to a randomly initialized neural network for the linear probing experiments. So that would be bad, for example. We would, you can also call these top lines and baselines as well. You would figure out, or like you would think about, okay, what could be a minimum viable proof of principle? So what could be the smallest experiment that we can do that shows that our idea makes sense and that it's right? And then it's always important to compare and contrast it to existing ideas. Like, why might it work? Do we have any previous evidence of other works that this sort of thing could work? Why might it not work? And what are the principles at play here? And of course, you kind of go over these things multiple times, so it's really not a linear process as I'm writing it out here. And yeah, next time I'll talk a bit about when to give up and when not. For that, actually, the guy in the top right, and I'm always having some researchers. Last time it was Rosalind Franklin who contributed to fundamentally to the discovery of the DNA structure. This time it's Isamu Akasaki who invented the blue LED, which was super important because that one was the one that was missing, so you could actually do white LED light, which is now, of course, all over the place. Yeah, it's pretty interesting because he was working on this project alone for 25 years until it worked out. So not necessarily my recommendation, but it shows you a bit of grit. And he had this inkling. He had this like scientific intuition that it will work, and it of course did at the end. Yeah. All right. So, all right. Now we're going to talk about RCNNs and fully convolutional neural networks. It looks worse than it is. It's actually quite simple. All right, so RCNN stands for region-based convolutional neural networks. The goal of an RCNN is to detect objects. And by that we mean, first of all, give us bounding boxes. These are boxes which contain objects, and give us the name or the category ID of what's inside there. Yes?
One question about these funny moments.
Uh-huh.
Because, like, in our field, it's like always about state-of-the-art values, or at least those are the values that you mainly look at. And sort of the chances that you build a network and somehow you get state-of-the-art on some data set are very, very small. But like, there are at least, or I hope there are some in-between steps where it's like, yeah, okay, this is working not better than state-of-the-art, but maybe it's like working at that scale fairly well. Like, how do you get these funny moments? Like, what kind of experiments maybe?
Well, I mean, one note there is like it's sort of not many people are working on new architectures, and I recommend that you don't really, because it's a really crowded field. It's really difficult to compete against others that have much more GPUs. But even there, what you would that's funny moments wouldn't necessarily be like you try something completely new, but you look at, for example, how things are done in NLP and see that they solve a particular problem like this, and you try it out and see it doesn't work at all if you do it in computer vision. And then you figure out, okay, but it's the same sort of basic idea. Why doesn't it work? Something like that. So you need to take this very, very broadly, basically. All right, and this task, is called object detection. And And the RCNN creates, first of all, these bounding boxes, or also called region proposals, using a process called selective search, which you might have had, I think, in computer vision 1. Doesn't really matter too much. It's a fairly old school technique, which looks at the image, so really the raw RGB values, no neural network applied or harmed there, at different sizes, and for each size tries to group the pixels together. And it basically, at the end, gives you, for every image, thousands of potential boxes, ordered by how likely they contain an object, basically. And thousands of boxes sounds like a lot, but you could calculate how many boxes you can fit into a 200 by 200 sized image. It's a lot more, actually. So it's just, it's still a lot, of course, 2,000, but the potential amount of boxes you have is really a lot. So you cannot obviously solve this as a pure classification problem if you were thinking about it this way. So the RCNN architecture looks as follows. So once you have these proposals, it takes the stuff that's contained in these proposals and makes an image out of that, right? Which is easy enough idea. And then you simply apply something like an AlexNet on top of it, and then it should say, okay, what is depicted here? Is it a plane? Is it a person or TV monitor? Yes, no. And if it isn't sure about anything, it might not be an object, basically, right? So that's like a really simple procedure, and that's why it also basically came out, I don't think I have the date here, but it came out just a few months after the whole deep learning started, basically. It was really the next obvious thing to do, in a way. What they also did, even in that paper, is now that they found the object in the box, for example, now you're sure there's a horse in the image, you can further improve the bounding boxes, which is done by a simple linear regression step. So this linear regression, now the output is simply offsets from the bounding box coordinates. You simply add this to the original proposal coordinates that you had, and you can slightly improve the localization performance of these bounding boxes. So the RCNN has these following steps. You generate a set of proposals, you run the images, you warp these images, and then you run them through a pre-trained backbone, and then you simply look at what image is in the box. And you have this additional step of linear regression to give you slightly better coordinates. And of course, it goes without saying that you need a training data set for this. You cannot train this on ImageNet. This method, you cannot train on image level labels. You need to have a data set which contains bounding boxes and the label of what is being depicted. Because only then can you, of course, have something like a linear regression model, or only then can you figure out whether something that's being depicted is actually being depicted. RCNN, when it came out, was quite cool, but it was very slow. Yeah? Right, so let's say you have your image, and you had like these 2,000 of boxes, right? And now every box sort of gets warped into like a default sized image, and then you apply your convnet on this. And let's say this one says it's an object, it's a dog or whatever. What you now do is, okay, maybe this box wasn't as good, right? Like maybe you're seeing that if it's a person, maybe you're seeing something like this. So you can say, okay, based on what I'm seeing, perhaps we should decrease the height slightly. So perhaps we should adjust the box a bit. That's all it does, and it improves it. Yes.
Are RCNN restricted to box, like to rectangular, or if you change to radius instead of like circular?
So the answer is boxes, because selective search gives you boxes. That's the main thing. Yeah.
that tightening, would you just try to like keep on increasing the confidence of the network until you hit a local maximum, or would you use some other way of doing it?
Well, I mean, similarly, for example, if indeed this is your training data, right? So this is like the ground truth, then obviously, and this would be, for example, let's say the output, then obviously you want to get this as close as possible to the ground truth. That's one thing. And another thing is also like now if you do this for the same procedure, you want this to say like no object. So you have both of these things going on. So you're not only increasing the confidence of the stuff that you're detecting. Yeah?
Is there an implicit assumption that the smaller the bounding box like area is, the better the solution is until you start missing, or until your confidence goes down?
No, I don't think so. If you're predicting like such a small bounding box, then you will have a very large error to the real bounding box, right? That's in the end. So I haven't written down the loss, but the loss will obviously contain the difference of a bounding box to the ground truth bounding box. So it won't go to that. Right, it's very slow though. I mean, I mentioned these 2,000 proposals. The method, the selective search is pretty fast, but then applying the CNN for everything, all of these things is pretty expensive. So that's 2,000 forward passes, right? And you have this really ugly pipeline of having 3 different models. You have the CNN, you have the classifier, you have a regression model, and you also have the selective search, actually. That all makes it really difficult to train, but it was a groundbreaking paper because it was done they solved this task or showed that neural networks can help with this task for the first time by a lot. So the next innovation was fast RCNN. So the architecture looks as follows. And the first insight was ROI pooling. So the idea is for the forward pass of the CNN, remember we're getting like 2,000 of these boxes, which look like this, basically. A lot of the computation is done with almost the same images, or at least you have a huge overlap in regions. So the idea is, let's just run this whole image through the CNN once, and that way we share the computation for the 2,000 proposals, and then try to find the regions in the latent embeddings. So it looks as follows. So in order to get the representations of what's inside these boxes, you throw the whole image through the network, obviously without these bounding boxes depicted, and then you take simply these bounding box locations in the final layers embedding. And note that VGG16, the default has a max pooling at the end, right? You just threw that away. So you're basically cutting off the VGG16, the regular version, at like one layer earlier before you do the whole pooling operation, which means you're still having the spatial extent. That's of course like the whole important thing if you're trying to do something like object detection. And so now you're simply taking, for example, for the left cat, you're saying the features for that box are the features which I'm taking from the latent space inside that box. Yeah. So that way you save a lot of computation, and yeah, so we only need one forward pass. Yeah, question?
Isn't it quite surprising that that works? Because like finding the same bounding boxes in the feature space, like somehow suggests that there's like the topology somehow capped.
Here the proposals are, the selective search is not that slow. Selective search is still run in RGB space, but you're simply doing the proportional crops in the embedding space. So selective search is not run in the embedding space. You're simply taking these locations. for example, if the topmost box starts at 1/4 of the image and goes all the way to 3/4 of the image, you're taking this and doing it the same in the embedding space. Yeah, yeah, exactly. Yes?
So why do we remove the pooling, did you say, in the last layer 18?
If you don't remove the pooling, what you'll have here is a 1x1 vector. And on a 1x1 vector, you won't be able to get like the corresponding crops. Yeah. So if you're doing anything that's spatial, or we call it spatially dense sometimes, the pooling doesn't make sense. Like if you're doing image level or later on video level stuff, then you typically use pooling because then you're just saying cat or dog or something, and then you might as well pool all the information in the image. But if you're doing stuff like that, you want to keep the spatial information alive. All right. Yeah, so that's how it looks zoomed in. How does this ROI pooling work? So basically, let's say these boxes look like following. What you do is you will always pool them back to a 3x3 feature map. So it looks like you simply do it like this. So you simply do max pooling in such a way that you end up at a 3x3 feature map. So depending on how big your box is, let's say it's 4x6, you simply pick the max pooling filter sizes, in this case 1x2, in such a way that you end up with a 3x3 feature map. And that way, you're getting one feature which has the same size for every bounding box, no matter what. Right, and the other thing that FastRCNN did was it combined all of these things into one neural network, which of course makes it a lot faster. So you can see it here. You can see this deep ConvNet gives you this spatial feature map. The ROIs are simply projected into this one. And then you have this pooling layer. And from there, you have, first of all, the output softmax, what is being depicted, basically. And you have the bounding box regressor. So all of this is coming from like one backbone, one deep embedding. So the overall steps, we can quickly run through them. So you process the whole image up to conv5. You compute the possible locations for objects using selective search in the RGB space. Of course, some will be wrong. A lot of them will be wrong, indeed. Given a single location, you do the ROI pooling to find a feature. And here we're writing fixed length because, again, if it's 3x3, you can always unroll it to a 9 by whatever the dimensionality is. If you do the unrolling always consistently, you simply can talk about it as like a feature, right? You don't care too much about the spatial extent of this 3x3 anymore. It's simply a feature for you at that point, if it's always what you're extracting is the same. Based on that, you have this bounding box regressor loss and the classification loss. Yeah, and that's pretty much what FastRCNN does. It also introduced a bunch of hacks, actually, to be better able to train, which is that it constructs mini batches in a way that that the number of bounding box locations is kept the same, so that you don't have one image which takes a lot of time and another image which doesn't take any time at all. So that allows you to speed up. Some results, and they're not, you can see some of them are, for example, not perfect. Like, for example, the cocktail shaker in the middle. The dog is not, some of these bounding boxes, bottom left, for example, the cat is being identified as a dog. So back then they weren't perfect yet, but it was, again, like a huge improvement over FastRCNN because it was much more accurate back then, and it was way faster now. However, you still needed those external bounding box proposals. So what comes after FastRCNN? faster RCNN. So they weren't extremely creative with all of these names, but it indeed made it a lot faster again, this next improvement. So the region proposal network now became the bottleneck, the selective search thing that we talked about, that fast RCNN was still doing in RGB space. The good thing one good thing was that you could simply run it on a data set and save all 2,000 locations. So you only had to run it once. That was good. But still, it was fairly slow to do. And the question is, can you not do it better if you use deep features instead? So can you not maybe do it better if you adapted selective search to run in a deep space, in the deep embedding? So basically that's what they did, and they called it region proposal network. So again, you start with the input, the image, you have conv layers, now you have a network which generates these proposals based on the deep features, region proposal, and then you have the same stuff that we talked earlier about. So now the proposals are generated from these deep features. And here actually you can see that the conv layers are depicted in a way like a box to show you that the spatial extent is more or less kept. Of course, it's not exactly, let's say, 500 by 500 anymore. That would be way too much. But at least it keeps the spatial dimensionality, of course, much more. Right, and how does the region proposal neural network work? It outputs probabilities. So it has a set of fixed bounding boxes. So it does it via classification. It says how likely does it think this particular bounding box is fitting. So it does it simply via classification, and it also fixes it by regressing from this bounding box that it's proposing, which are the aspect ratios here, I think. Yeah, so basically you have a network which does this in deep space. It looks like the following. You have these K anchor boxes. So these are all the different shapes and sizes. And for every location that you're applying this neural network, you're applying this neural network on top of a feature map. You're sliding this across the feature map. And at every feature map location, it's saying, OK, which box do I think would be right to be applied at this location, and what should be inside this box. So that's the classification layer. And yeah, the 4K coordinates. So if you have K box proposals, it could say, yeah, it picks one of them out of that. Right. And finally, mask RCNN. That's another upgrade, but it's actually like one of the simpler upgrades with like pretty impressive results. So what they've been doing, what we've been seeing so far is simply bounding boxes, right? The question they asked here was whether you can extend it and actually locate the pixels that belong to an object. So this would be the task called semantic segmentation. Or image segmentation. And the question is fairly simple. Once you have bounding boxes, and these are really good, can you now simply color in the pixels that belong to the object and not color in the pixels which don't belong to an object, right? If you already have solved the problem of object detection, then image segmentation or object segmentation becomes pretty easy. And the way this is done is by simply taking this box where we are sure that there's an object inside, and now we're simply going to predict a binary mask that says for every given pixel in this mask, or for every given pixel in this box that we got, whether there's an object present or not. So this additional neural network, which we add to the faster RCNN pipeline, is simply using the CNN feature map and outputs a matrix with ones or zeros. And again, you as you might have realized, this now needs a new set of training data, right? Now, our previous training data simply had to have boxes around objects. Now, in order to train this with ones and zeros, our training data needs to actually have like it colored in that these pixels all belong to a human, and these pixels, for example, belong to the background. And you can also see why that gets slowly and slowly more expensive. Like, you can do this for a couple thousand images if you're a company and you have money, but now think about video, right? Like, if you have to color in, have human annotators do this for video, it starts to become more and more unfeasible, which is also partially why we'll have the lecture on self-supervised learning later on in this term. But going back to this, so the basic idea was the following. So you take this faster RCNN network, and then you simply, again, use the features, use the deep embeddings, and then you apply a neural network on top of these. So first you upsample the spatial resolution to 14 by 14, and then you train this mask. And then if the mask, for example, if your network will operate on a 14 by 14, and if your mask is, let's say, 80 by 100 in terms of pixels in the output space, then you will simply rescale that, just like if you take an image in a computer and you change the width, and then you will make it fit, basically. Yeah?
I still had a question about the faster RCNN.
Mm-hmm.
So we are learning now sort of these boxes of the selective search. I was wondering if the boxes that we find are similar, or if they're actually finding very different types of boxes.
Good question. I'm not sure. They're definitely both finding stuff that's close to the ground truth, because they, in the end, can train. How close the top 2,000 proposals are, I think there's an experiment in the paper, actually. Question two there? Yeah. Yeah.
So we saw before that with the faster RCNN, the bounding boxes were not always perfect.
Mm-hmm.
So in this case with the mask RCNN, will the masks be bounded maybe by predicted box limits? Or is it something?
That is precisely correct, yes. Yes. You could say that now that you have a data set which will have these image segmentations, now you're getting better gradient, like even stronger signal, right? It's kind of like the more information you're giving, the more supervision you're giving, the better signals you're getting. So that can also help the bounding boxes actually go closer to the ground truth. But just before I'll show you the results, that will actually look a lot better. What they changed is they changed ROI pool to ROI align. So ROI, again, it stands for region of interest, which is what could become a predicted bounding box or could, in the end, not be one, depending on the result of the neural network. And what they did is, what they realized is that this ROI pool doesn't exactly match the feature map. It was slightly misaligned, basically due to rounding errors, etc. And what they did instead is they removed this rounding. So instead of, for example, if the bounding box was, let's say your feature was a 5 by 5 grid or something like that, and your region proposal network said, oh, I believe there's a bounding box here. So obviously these are not exactly, or in the case if we're talking about centers, let's say it said we're here. Then it's not quite correct to take the pixel value, which is, or the feature map value, which is exactly in the middle, but also not good to take this one instead, if we're saying the features exist in the middles. Instead, we should probably take a feature which is somewhere between this feature and somewhere between that feature, somewhere in the middle. And this is exactly what they did. They did simply linear interpolation between the features, and that's how they took the feature. And that was more accurate. It's called bilinear interpolation. That's what they did for this one, and that allowed them then to get these pretty nice looking results. Yeah. And nowadays, this method has been even further improved. All right, then the final part is about fully convolutional neural networks. We've sort of briefly hinted at this already, that if you simply remove the pooling, you can keep a spatial extent. And also something that we talked about in the AlexNet lecture is if you then do a 1-by-1 convolution, which gives you a 1,000 dimensional feature map, and it was trained for classification, you can actually sort of visualize where something is present, right? You can train it by simply, after this 1,000 dimensional, 1,000 by some spatial dimensional thing, you can simply pool it and then you train it. That's what we had in the AlexNet lecture. But then at evaluation or time, you can, for example, visualize, okay, where does the cat neuron get the highest activations, and you can do this sort of stuff, for example, which is nice. But the question is, can we do more than that? So, for example, when we go deeper, can we do some upsampling again? Because we want to, for example, do some better segmentation than this one. And here the idea is we will use something that's called deconvolution or upconvolution, which basically, via the use of a lot of padding, has an output map which is bigger than the input map, as you can see here. And if you use that, you can go from a small representation, so you can first use a neural network which gradually decreases the spatial extent, as we saw with all of those poolings and so on, right? And then gradually increase it again, which will allow you to get these sort of output maps. And then if you do end up at the spatial resolution, right, then you can apply simple pixel-wise losses. So it's almost looking like some sort of autoencoder, but instead of the loss being on the pixel values, it's simply on the semantic segmentation mask values. All right, so you have, for those that have a tutorial straight after this, you have 12 minutes. If you have questions, please come to the front. One thing I wanted to mention is, so this was lecture 6 now. We're sort of close to the halfway mark. I would encourage you to, of course, I mean, with the assignment, you've seen the Canvas stuff. But also don't forget to read up on the lectures and don't wait until just before the exam to keep up to date with the lectures. What we do today, what we did last week, it almost always builds up to the next lecture. So yeah,